Hello, and welcome to our last edition this semester of audio-video lectures in astrophysics. Our last topic is going to be an introduction to dark energy and the accelerating universe. This is found in sections 8.3 at the end, and then again in 8.5 picking up. So we'll start in 8.3. And I'd like to revisit the idea about a radiation-dominated universe and a matter-dominated universe. What's important to see here is that the densities, as they vary with the scale factor, are not the same. So I draw your attention to equation 837, where you see that the density goes like scale factor to the -3, whereas in the radiation-dominated universe, the density goes like the scale factor to the -4. And I'd also like to draw your attention to Mauss's statement right under equation 845. Since the energy density of radiation falls faster with R than that of matter, at an early enough time there must have been a radiation-dominated era, during which rho goes like R to the -4, the scale factor. And so what we're trying to understand here is that there was a time in the universe when the radiation dominated over the matter. We see that as evidenced in the cosmic microwave background. And then, as that relates to dark energy, we think about in the future, it is possible that there could be some other component that dominates the universe's dynamics. Maybe not even radiation or matter, but something else other than that. And I think that's really the crux of looking back and seeing that at some point the radiation dominated over the matter. And then also, if we draw our attention and look at equations 850 and 851, you can actually see that at time 0, if R of t goes like t to the 1/2, as in equation 849 in the radiation dominated era, then at t equals 0, R equals 0. Therefore, the scale factor equals 0, and we have an infinitely small universe. Similarly, if we take the limit as t goes to 0 of rho of t, that's the energy density or the mass density of the universe, we see that that goes like the scale factor to the -4, which says that if R of t goes to 0 at t equals 0, then 1 over 0 to the 4th power is going to in fact go to infinity. And if the density goes to infinity as the time equals 0, then that would be our definition of singularity. And it is equations 849, 850, and 851 that tell us that there is something called the Big Bang. With that background given, as we think about the past, the universe in the past, at earlier and earlier times, we now can move into the future and think about how does the universe evolve as we move forward into the future and the end, as it would be, of the universe. And that's section 8.5. Section 8.5 has some discussion initially about a cosmological constant. We've referred to this at various times. This is sort of the source of dark energy terms. And in 8.5, we're going to consider what are the effects of having this cosmological constant. To understand the origins of the cosmological constant, why Einstein introduced it, and why it hasn't gone away, I refer you to some articles that are on Inquire that relay the history, and even your own Heart of Darkness textbook or book allows you to understand somewhat the history of dark energy. So we'll go ahead and start with the introduction of the Friedmann equations and the third equation, which is the energy conservation equation. That's 895, 896, and 897, with these cosmological lambda terms already explicitly placed in them. So you'll see that 895 and 896 have this lambda over 3 term added on, and you'll also see that the energy equation, the energy conservation equation, is unaffected by the lambda term. That makes things a little difficult in terms of observation, as we've already seen. But I think the important takeaway here is that if you look at a term at the equation 896, where you have an acceleration term r double dot, we talked about earlier where r double dot had to be negative, as given by this leading minus 4 pi g over 3 c squared term. And that makes the entire deceleration always intact, except if we have this positive lambda over 3 contribution. We could in fact have a large enough contribution from lambda to overwhelm or thwart the deceleration and could give us a positive acceleration from the R double dot term. I think that's a huge takeaway here at the outset before we even talk about what exactly is the nature of dark energy or what is the vacuum energy that Moz refers to. And we'll do that toward the end. But I think the most important thing right now is to understand clearly that if the R double dot term in the past, as we consider a non-cosmological constant universe, always was fixed to decelerate, if we add in this lambda over 3 term, we could in fact make it large enough that it could give an overall positive acceleration to the universe. Another extremely salient point that Moz makes is that if the energy density is given enough time, so notice how the mass density and the radiation density will by default and by definition, as the scale factor grows, mass density will decrease. So if you think about given a certain constant of mass energy in the universe, namely the conservation of mass and energy, as the denominator continues to get larger and larger, the overall contribution of the mass density will decrease in its overall amount. So if we live in an expanding cosmos where the scale factor is always growing, then in effect, if the other terms are decreasing in their effect, by de facto, if the cosmological constant is in fact a constant, the energy density due to this cosmological constant will in fact dominate in some epoch. And I think there's a great figure that I'm drawing your attention to now that shows that if we had a radiation-dominated universe early in the cosmos, and then we lived in this matter-dominated world that we have up until the very recent present, then as the universe expanded enough, R grew enough to allow for the cosmological constant to be the dominant force and be the dominant pressure contribution, the energy density contribution in the universe as we currently see it. Before moving on to a small piece about what is the nature of dark energy, I think there's one other set of equations and a flow of thought that's worthy of pursuing, and that begins with equation 8102, so 8102 on page 206 or so. And so with this particular model, we start with the Friedmann equation, where we have r dot over r squared, which now in equation 8102 is just h squared. That's the value of the Hubble parameter at a given time. And then the entire equation is divided by h naught squared, which is the current value of the Hubble parameter as measured in the current epoch or at a redshift of 0. Then what we do, or what is done, is to substitute now the critical density. Remember, the critical density is derived from omega matter, which the critical density is the density in the universe that is required so that we would have enough gravitational energy to collapse or to close the universe, so that at some point in the future of the universe, the mass density would be gravitating enough to cause the universe to stop in its expansion and to then start to contract. So once we substitute that, then we're able to rewrite equation 102 in terms of the density divided by the critical density. That gives us our parameter omega matter, which is defined in 8105. In the past, we've just had the dimensionless density parameter, omega m, which stands for omega matter, and with the addition of the lambda term in 8104, we now have this extra dimensionless parameter for lambda, which we refer to as omega lambda, which is the fractional contribution of the density of the universe due to the lambda parameter, the cosmological constant parameter. So now the equation becomes a sum where we have in 8107 omega matter, the density parameter, dimensionless density parameter due to matter, plus the dimensionless parameter due to the cosmological constant equals 1. And we therefore are able to make that statement in 8108 for any epoch, not just for the current epoch, but for any time. And therefore, if k equals 0 and we have a flat cosmos, we will always have the sum of these two contributions equal to 1. That tells us then that those parameters can change over time, that the actual fractional contributions over time can change, and therefore we can have lambda changing as a function of time, matter density changing as a function of time, so long as the sum is always equal to 1.